Let us start with what we have did in the previous lecture. In the previous lecture, we have discussed regarding this graph, subgraph, then proper subgraph, spanning subgraph. We have discussed some operations on a graph, which involves the union of a two graph, intersection of a two graph, a ring sum of a graph. Then we have seen the how to delete an edge and the vertices from the graph. We also seen the how to fuse a two vertices in a graph. So I think so we have covered this much in my previous lecture. As I told you that we'll discuss regarding the walk, tail and path in this lecture. So let us define what is a definition of a walk. A walk is actually a graph in a G, and it is a finite sequence of vertices and edges. So what I can write, a walk in a graph G is a finite sequence W. It's generally denoted as W. Walk is denoted as a W. Is a finite sequence of vertices, that is V0, and edges E1. Then again vertex is there, V1, E2, V2, E3, up to so on, Vk minus 1, Ek, Vk, whose a term, so in this is a finite sequence whose terms are alternatively vertices and edges. Such that, in such a way that for every k which is, so every I which is in between 0 to k, the edge ei has endpoints or end vertices and vi minus 1 and k. So this is the definition of a walk. Let us give you example. If I consider this is the vertices, and if I consider this is as a graph, any graph you can plot. It's up to you how you are plotting. So it is depends on how you are doing it. So these are the vertices we have here. So I will say the vertices are V1, V2, V3, V4 and V5. And the edges is E1, E2, E3, E4, E5, E6, E7, this is E8, E9, E10. Okay. Now this is the graph. This is the graph G. Now what is walk here? So as per the definition, is a finite sequence of alternatingly vertices and edges. So you can start with any of the vertex here. Let's say I'm starting with V1, and then you can travel with any of the edge which is incidence with V1. So let's say I'm traveling to E9, then we'll reach here V3. So there is V3. Then V3, you can travel on V3 by any incidence vertices of that or incidence edges of that. So let me travel with E10 and come back at the same position V3. Then we travel by E5, then to V2, then E4, V4. So this is a walk. A walk is this. So this is an example of a walk. Okay. So what is each EI is immediately precedes and successor of two vertices which are incident to the vertex, the edge EI. This is known as, or this example, I can say it is then edge. Sorry, this is a walk V1 to V4. In particular, in here, we'll say it is a walk V0 to Vk. So this is a walk. I can say W is a walk V0 to Vk. It is the notation for that. It is a walk V0 to Vk. So for example, here you just say that a W is a walk from V1 to V4. Here V1 it's called the origin. In particular, this V0 it's called the origin of the walk, and Vk is terminus of the walk. So the V0 here, V1 is a origin, V4 is a terminus. And V0 and Vk need not be distinct. Need not be distinct. It may be same or equal. It depends. The internal vertices. That means this V1, V2 up to Vk minus 1 are internal vertices. What we'll say is V1, V2 up to Vk minus 1 are internal vertices. See, word itself suggesting its definition. Okay. So here in particular, V3, V3 and V2 are the internal vertices of the walk W. Now the next definition is a length of walk. A length of walk is nothing but the number of edges in a walk. Number of edges in a walk, it's called a length of a walk. Let me write the number of edges in W, it's called length of a walk. It is denoted as mod W. A mod W is a notation for this. So in particular, for this walk, a mod W is equal to 1, 2, 3, 4 is 4, because there are 4 edges are there. So that's why it is the length of this walk is 4. One should note that in a walk, W, the repetition of edges and vertices will be there. Okay, so there may be a repetition of vertices and edges. Okay. Now the next definition is a trivial walk. Trivial walk is a walk containing only one vertex, no edges. Okay, a trivial walk is one containing no edges. So in a walk there will be no edge. It's called the trivial walk. For example, W equal to V. So what is the length of a trivial walk? 0. In particular, I can say a length of a walk is 0. It's called a trivial walk. So I have obviously give you example of a trivial walk. If the end vertices, that means the origin and the terminus is the same, then it is called a closed walk. And if it is different, then it is called open walk. Okay. So if I can say closed walk, first of all, it is a walk. A walk UV, it's called closed if U equal to V. Open walk, a walk UV, it's called open if U is not equal to V. So that is the definition of a closed walk and open walk. For example, this W1, if I can say, a W1 is a open walk or closed walk? Open walk. Okay, so I can say that W1, for example, W1 is an open walk. Let me write W2 as a closed walk. So in this graph G, if I start with V5, that is V5, then V5 goes with V2, E3 V2, then E5 V3, then if it is reached to E7 V5, E7 V5, since origin and the terminus is same, W is a closed walk. Is an example of a closed walk. Now the next definition is a tail. When we can say it is a tail. So if each edge in a graph is a different, then it is a tail. In a walk, every edge is a different, then it is called a tail. If the edges E1, E2 up to EK of the walk W, that is V0, E1, V2, E2, V3 up to Vk minus 1, Ek, Vk, are distinct, then W is called tail. That means, in other words, I can say it is a walk in which no edge is repeated. If the edge is not repeated, that walk, it's called a tail. For example, W2, which we have defined here, is, since there is E3, E5 and E7, their all edges are different. W2 is a tail. What about W1? W1 is also tail because it has E9, E10, E5 and E4. So I can say that W1 and W2 are example of a tail. But if I can say W3, which is V1, E2, V2, V1, E2, V2, then it is V5, E3, V6, E3, V5, E6, E3, V5, E6. Then again V1, if I can write V2 again and then V2, then this E2 is repeat. So this W3 is not a tail. It is a walk, but it is a not tail. Okay, so this is the example of a tail and a walk which is not tail. The next definition is a path. So what is the definition of path? In which the every vertices are different. If the vertices V0, V1 up to Vk of the walk W, that is V0, E1, V1, E2, V2 up to Vk minus 1, Ek, Vk are distinct. Then W is called path. Okay. So what will be the path in the above examples we have discussed? Is this V3 is a path? V3 is not path because the vertex V1 is repeating. V2 is a path, V2, V5, V2, V3, V5. V2 is also not a path. What about V1? V1 is a path because V1, V3, V3 is also repeating. So V3, W1, W2, W3, all of them are not a path. They are not example of a path. I can say that W1, W2 and W3 are not path. They are walk but not path. Let me define W4. So if I define a W4 as V1 until here, V5, if I define it is as V1 E2 V2 E3 V5, then it is a path. There is no repetition of vertices is there. One should also note here, if any two paths with same number of vertices are isomorphic, that means if the path having the same number of vertices, here W4 is V1, V2, V5. If you write down any other W5 which having the same number of vertices in it, let us try to draw or try to write down V5, E3, V2, V5, V3. Okay, so we'll start with V5, E2, and what I said, V5, E3, V2, E3, V2, then E5, V3, E5, V3 is a path. Here I can say that W4 and W5 are isomorphic path. Okay. A walk, a path with n vertices will be sometimes will be denoted by Pn. Path with n vertices is sometimes denoted by Pn. So I may ask you a question, what will be the length of Pn? The modulus is represented as a length of a walk. I can say the length of Pn. What will be the length of the Pn? If Pn contains n vertices, so how many edges? A length defined as number of edges in the walk. So it is n minus 1. You can just see that number of vertices are 3 here. The number of edges will be 2. So it is the length of the Pn will be 2. For this it is in general, it is n minus 1. Now there will be two terminologies here. Our first one is a path, another one is a tail. What I can say, every path is a tail or every tail is a path. Obviously, a walk is there. A walk characterized into two parts. Path in which no vertices is repeat. A tail in which no edges will repeat. Now, there is a things that every path is a tail or every tail is a path. So, is this true? Or this will be true? What is your conclusion?
Every path is a trail.
Yeah. So the first one is true. The second one is not true. Because a path is a walk in which no vertices repeat. If the no vertices is repeat, no edge can be repeat either. Okay, so I can say that every path is a tail. Every path is a tail, but the converse is not true. That means every tail, sorry, here I have written the same thing. Na? This should right. But every tail is not a path. What is the example? If I can write W3, sorry, what is the number? It comes before W6. If I write W6, W6. If I write V1, now you can see the figure in front of you. Then V1 it is E6, V5, V5. Then you will go to the E3. V2, then V4, it is E4, V4, then you will go to V3, that is E8, V3, and then from E3 you will go E9, V1. So what is this W6? Is a path? Or not
Yes,
a path?
it's a path.
What is the definition of a path?
No vertices will be repeated.
Vertices will not repeat, and edges will also not repeat.
So what about V1?
Oh, sorry, there is
Yes,
V1
yes,
is repeated.
So
It's not a
W6
path.
is not a path. Is W6 is a tail? Edges are different. So W6 is edge. Sorry, tail. So that means every tail, this is a tail but not path. So that means this W6 is an example of the converse is not true. That means every tail will not be a path. So now I hope you guys have understood what you mean by walk, tail and path, because this is very important concept in many of the applications is needed. Then the next definition is a connected graph. So what is your intuition says about the connected graph? When I can say a graph G is connected? So every vertex U is connect, or I can say, let's first define a connection between U and V. So a vertex U is connected to a vertex V in a graph G if there is a path in G from U to V. So if there is a path exists from U to V, then I can say U and V are connected. Now using this, I can give the definition of connected graph. So this is about two vertices are connected. So what should be the definition of a connected graph?
There should be a path passing through all the vertices.
So every pair of vertices are connected. Or what you are saying is every two pair of vertices have a path in between. Okay, so you can write a graph G is connected if every two of its vertices are connected. Then what do you mean by disconnected graph? So this is a definition of a connected graph. What is the definition of a disconnected graph? A graph which is not connected. Graph that is not connected it's called disconnected. For example, you can give the example of a connected graph and disconnected graph. So if I can say this is the graph, if I can draw in this manner, if this is the graph G, then I can say G is connected graph. And if I have a graph like this is total graph G1, then G1 is disconnected graph. Why it is disconnected graph? Because this vertex will not have a path between these two. So that's why it is called the disconnected graph. So it is, I can say it is a component of two connected graphs. This is a one graph which is connected. This is another graph which is connected. Okay. So from this we can make one statement, that is a graph G is disconnected if and only if its vertex set V can be partitioned into two non-empty disjoint subsets V1 and V2 such that there exists no edge in G whose one vertex one end vertex is in subset V1 and another in subset V2. So this is the statement. You just understood what is the statement means. If the graph G is disconnected, the graph G is disconnected, for example this, then a vertex set of V of G. So this has five vertex. This graph has a 5 vertex here. That is A, B, C, D, E. So the vertex set of this is A, B, C, D, and E. As per this, it's saying that the vertex set V is partitioned into two non-empty disjoint subsets V1 and V2 in such a way that the no edge in G whose one end point of that vertex is in V1 and another one is in V2. That means I can partition into two. This is disjoint, so I can have two subset of this V1 and V2. So I can partition into A, B, C, and other set is D, E, so that there will be no edge in the graph G whose one end point is in this set and another one is in this set. So that is the meaning of this statement. Okay. One more theorem that I can state here is, if a graph has exactly two vertices of odd degree, there must be a path joining between those two. So that means a graph is there who has exactly two vertices of odd degree. Then there must be a path joining by that. Okay? And this is easily proved by handshaking lemma. For example, I can a graph with what is this says that a graph has exactly two vertices of odd degree. Then there must be a path joined by these two vertices. So if the graph is there who has two vertices of odd degree, then there will be a path. Suppose I am proving by negation. That means all the vertices of even degree. Then by handshaking lemma, what we can say? Every component of disconnected graph, no graph can be odd number of odd vertices, because handshaking lemma says that there are odd number of even vertices. But if all the number of is there, and so the V1 and V2 belongs to a same component, and hence there will be no path. So you can just see the proof. I'm not discussing the proof here, but it is easy to see this proof that I'm giving you, as you can discuss with that. The next one that we'll discuss in the next lecture, the next theorem, that is says that a simple graph with n vertices and k component. What do you mean by component? In this disconnected graph, there will be two components. The first one is A, B, C, D, containing that. Another one is DC, DE. So this disconnected graph has two components. Then the question is, if the graph which having n vertices and k component, how many number of at most edges will be there? So can have at most space edges. You can fill this space in your free time. I will ask you tomorrow what should be the things should be there. Okay, fine. That's it for this lecture. You can leave